For thousands of years, people have used the energy produced by moving water to perform tasks such as grinding grain and sawing wood. During the 20th century, the energy produced by moving water helped spur industrial development by powering textile mills and manufacturing plants. 1775. In the United States, the Army Corps of Engineers was established. Their responsibilities evolved to include planning, designing, building, and operating dams. 1880. The United States' first industrial use of hydroelectric power began when 16 brush arc lamps were powered using a water turbine at the Wolverine Chair Factory in Grand Rapids, Michigan. Soon after, hydroelectric power began to be used in other countries as well. 1882. The world's first hydroelectric plant began operation on the Fox River in Appleton, Wisconsin. 1920. The Federal Power Act established the Federal Power Commission, which had the authority to issue licenses for hydroelectric development on public lands. 1933. A federal agency, the Tennessee Valley Authority, was established. By constructing dams and hydroelectric power plants, the Tennessee Valley Authority brought electricity to one of the nation's poorest regions. In addition to controlling flooding and improving waterway navigation, the Tennessee Valley Authority's efforts resulted in increased industry and employment. Today, hydroelectric power plants continue to be a major source of electric generation in many regions of the world. Hydroelectric power plants range from giant dams that generate thousands of megawatts of power to small power plants that generate electricity using less water pressure than the typical household faucet. Hydropower plants take advantage of a naturally occurring, continuous process that involves the cycling of water through the environment. This process is called the hydrologic cycle. In this cycle, the sun heats the air, causing water from oceans, rivers, land, or anywhere there's moisture to evaporate. When warm, moist air rises, it carries this water vapor with it. As the air rises, it encounters cooler and cooler temperatures. This causes the water vapor to condense into fine droplets, which become clouds. If the air becomes so cool that it no longer can hold the moisture, the droplets fall to the ground as rain or snow. The rain or melted snow flows over the earth as surface water or through the soil as groundwater into streams and rivers. Gravity causes the water to flow back to sea level. Hydroelectric power plants convert the potential energy from this flowing water into electrical energy. Hydroelectric power plants generate electricity by converting the potential energy of water moved between two different elevations. The hydroelectric generating process typically begins when a control gate is opened, allowing water to flow to a powerhouse. In this example, the water flows to the powerhouse through a sloping pipe called a penstock. The water also may travel through a tunnel, chute, or canal. Inside the powerhouse are one or more units consisting of a turbine and an electrical generator, depending on the volume of water available and the design and purpose of the plant. Inside the turbine is a rotating wheel with a row of curved blades called a runner. The runner is located directly in the stream of water that flows through the hydroelectric power plant. In this type of turbine, the water rushing in through the penstock enters into a large circular tube that surrounds the runner. This tube is called the scroll case. Wicket gates are a series of interconnected openings that operate in unison to control the flow of the water from the scroll case into the runner. The angle of the wicket gates controls the amount of water flow onto the turbine runner and can be adjusted from fully closed to fully open. When the wicket gates are opened, water enters the runner and pushes against the runner's blades. The water's pressure and speed cause the runner to turn. The water passes through the center of the runner and leaves the turbine through a draft tube. The draft tube is specially shaped to slow the speed of the water before it's discharged from the power plant. As the runner turns, it rotates a shaft that goes into the electrical generator. Inside the generator, the shaft turns coils of copper wire within a magnetic field, which converts the potential energy into electrical energy. The electricity from the generator passes through a step-up transformer where the voltage is increased and is then sent to transmission lines that carry it to homes and businesses. Several methods are used to harness water power for generating electricity. The method used depends on the area's geographic features and the water resources that are available. The water flow powering a hydroelectric plant sometimes comes from a reservoir or impoundment that builds up behind a dam on a river. Water is released from the reservoir for several reasons: to meet the need for electricity, to adjust and maintain downstream water flow for the protection of property, fish, and wildlife, to make waterways navigable, or for the safety of the dam. In other locations, some of the water in a free-flowing river or creek is diverted to the hydroelectric site some distance away through a canal, channel, pipe, or tunnel. This method of harnessing water power is called diversion, or run-of-river. A third method of harnessing water power to generate electricity is called pumped storage. A pumped storage facility requires two reservoirs, with one reservoir significantly higher than the other. When there's a high demand for electricity, water from the upper reservoir flows downward through the turbines to help meet that demand. After passing through the turbines, the water flows into the lower reservoir. When there's excess electricity available from other electric plants, this plant uses this excess electricity to power pumps that move water from the lower to the upper reservoir, so it will be available for generating electricity when the demand increases. There are two types of turbines used in hydroelectric plants: reaction turbines and impulse turbines. Characteristics of the water flow used as the source of energy determine which type of turbine is used. A reaction turbine uses the pressure and movement of water flowing over the surfaces of the runners or turbine blades to convert the water's energy into rotational movement. Reaction turbines typically are used in hydroelectric plants with a moderate to high water flow. The distance the water falls before reaching the turbine blades also is moderate to high. Impulse turbines are designed to work in hydroelectric plants where the amount of water flow is relatively low, but the distance the water will fall before reaching the turbine is substantial, sometimes more than 1,000 feet. Inside an impulse turbine are nozzles that convert the water flow into one or more streams of high-pressure water. These streams are directed against a series of spoon-shaped buckets around the outside of the runner, causing the runner to turn the shaft attached to the magnet within the power plant's generator to create an electric current. While hydroelectric power plants provide electricity without producing emissions, including greenhouse gases, other environmental issues must be considered. Reservoirs associated with hydroelectric power plants may cover thousands of acres of land and river habitat. The advantages of hydroelectric power generation must be weighed against the effects of taking land out of production for agricultural, forestation, or other uses. In addition, hydroelectric power plants can impact fish migration. Disruptions that can affect aquatic organisms need to be identified, minimized, and managed. For example, upstream fish passage can be aided by installing fish ladders or elevators, or by trapping and transporting fish around the dam. To assist with downstream fish passage, fish can be diverted away from turbine intakes with screens, racks, or even underwater lights and sounds. When diverting water for electric generation, enough water must continue to flow through any bypassed section of the river channel to ensure the survival of fish and other aquatic habitats, and to reduce algae and sediment buildup. Hydroelectric power generation provides other positive benefits in addition to providing electricity for homes and businesses. Since the water used for power generation is not consumed in the process, it continues downstream and can be used for other purposes. Impounded water behind dams can serve irrigation networks and supply domestic water, while helping to control flooding that might occur downstream. Lakes behind dams offer opportunities for recreational activities such as boating, camping, fishing, hiking, and wildlife observation. In some parts of the world, and particularly in the United States Pacific Northwest, Hydroelectric projects with storage capabilities play a critical role in integrating intermittent power resources, such as wind or solar energy, into the electrical distribution system as they become available. Natural resources must continue to be respected, and care always must be taken when balancing the potential environmental impacts of using these resources with the energy needs of current and future generations.